All right, everyone. Welcome to this afternoon session, which is the breakout session for fibrous materials. Great that you're here. Please take a seat, make yourself comfortable, and we will start in just a few seconds. And happy to have you here today. So hello, everyone. My name is Oliver Rimmel, and together with my colleagues, I will guide you through this session today. For my background, I'm a mechanical engineer, and I've worked at Composite Materials at the Institute of Composite Materials, very close to here in Kaiserslautern. And after that, I worked at PFW Aerospace in Speyer on additive manufacturing of aerospace parts. And since 2022, I've been with Math to Market, and I'm the business manager for the business area digital material R&D here at Math to Market. And this involves, but is not limited to, foams, composites, ceramics, metals, additive manufacturing, nonwovens, and technical textiles. So when you see, it involves fibrous materials in many of these application areas. And as I know, some of you are also coming from other applications such as filtration and electrochemistry, and we're very happy to welcome you here today. So during the session today, we are already in the introduction that I'm doing today. After that, my colleague Andreas Grieser will guide you through some examples on how to determine fiber length from an injection molded glass fiber reinforced composite. Then we will have a short coffee break to refresh everyone. And my colleague Lilli Burger will continue and show you some examples on how to get through a 3D model for nanofiber media when you only have 2D SEM images available. And after that, we will have the innovation exchange, and this is really about involving all of you into the discussions. It is about showing some ideas that you have, some applications that you're working on, and really finding out what will be the new trends that will be interesting for you. What should we develop for the next GeoDict steps? And we have had quite some very interesting submissions for this one, so we're really looking forward to that. And as mentioned, be prepared to be involved. Looking forward to that. As we've seen before, we have a lot of different modules in GeoDict, and we can do a lot of different geometries with that. And especially for modeling fibrous materials and also analyzing fibrous materials. So we have, of course, we are working with Import Geo here at the top on getting the CT scan inside the computer and inside the software. Then we have Fiber Geo to model fibrous materials. Also complementary to that, we have Paper Geo. When it comes to woven materials, we use Weave Geo very often. And of course, we analyze these structures using PoroDict and MudDict. And when it comes to finding fibers, to analyzing fibers, to really identifying single fibers, we use, of course, our FiberFind AI that you will learn about more later in this session. And when we're talking about composite materials, as mentioned before, the process often starts with digitalization of a sample. Could be a CT scan, could be in some cases even FibSem, or just using micrographs of the material that you have. Then we do a thorough analysis of that. Could be about the fiber materials, about the fiber length, fiber orientations, and so on, but just as well about the porosity of the material. And then we can validate that with physical measurements that we've conducted, for example, with mechanical properties, and we can start changing parameters and designing new materials. So a very simple example that we brought here today, which is quite nice in my opinion. We were talking with someone about some composite materials, and they were wondering how can they do some quality control on their composite materials. So we just modeled some very simple example of a 0-90-degree composite. And we have an app inside GeoDict that makes this quite easy. So it doesn't take too much effort to create a material like this. And you see, we even added the porosity into the material. So we get really realistic micrograph also of the material, like you would also encounter it in the microsections that you do from your samples that you have in your hand. And when you use that from a micro-CT and put it into GeoDict, you can analyze for the fiber volume content, which is really relevant for the mechanical properties. You can analyze the thickness of layers, which could be, for example, in filament winding, something that results from your winding process. You can have a look at the fiber alignment, which is also, of course, influencing mechanical properties, the fiber distribution, and you can also look at void control and void distribution. So On the one hand, this can be used for conducting quality control and really understanding your process. But as mentioned before, you can also use that to start modeling new materials. Some similar process for non-woven materials. Of course, we also start here very often with micro-CT scans, and we will also show an example later what you can do when you only have 2D data available of your non-woven. Also for non-woven, we can analyze the fibers, of course, for all the properties that could be relevant here. And as we will see in a very interesting talk tomorrow, you can also use this input here from the CT and from FiberFind AI and export that directly to other software such as Abacus. And just like as with the composite material, you can use this data, you can validate the properties from the physical sample. We've seen that this morning also in Adrien's talk. You can also validate that with, for example, the permeability that you get, and then you can start optimizing your material for the properties that you would like to have in your material. So it looks a little bit different, but the process in the end is the same. And this is like this for most of the applications in GeoDict. And here we have a nice example. This is an SEM image in the top here at the microscope that you see from a waterproof membrane. It could be something like a Gore-Tex that you have in your winter jacket when you go skiing. And when you have this image data available, you can also analyze the non-woven for the fiber basis weight. You can have a look at the amount of binder. You can look at the fiber orientations and the fiber distribution. And you can just as well look at the pore structure that is inside the material. And you can, of course, start by reproducing experimental measurements, but you can also have a look at how will it really influence the water tightness in this case for the membrane if we change some of the material parameters. And you can see here the water accumulates at the bottom of the membrane, and at some point there's a breakthrough, and we could calculate that this specific sample had water breakthrough at 4.5 bars, which is quite realistic for such a membrane that you would have in your ski jacket, for example. And you can see here also without the fibers. At some point it's not watertight anymore. Talking about the development plan, and we will come back again to this later, but just to plant the seed a little bit here. So in GeoDict 2026, which we have on the left column, we will work on improving the mesh export to use the data that you generate in GeoDict with other software. And we will also have a little bit more work on structure property optimization frameworks, as we've seen that before, for example, for non-wovens and their permeability, but you could use that for totally different examples just as well. And a topic that we will also work more on is automated generation of digital twins from not having all kinds of data that you need probably. So if you have a limited data set, how can you still get to a nice 3D model of the data that you have? And covering a little bit the years between GeoDict 2026 and 2027, we will be looking at how to generate 3D structures from available 2D data sets for grains and fibers. In GeoDict 2027, we will focus more on large deformations in ElastoDict and improve contact attachment. And on the longer roadmap, we will also have a look at more friction in deformations and contact styling, which is really asked very often by the customers. In GeoDict 2026, we will also start with implementing new algorithms to really identify objects on the grayscale images that we have. So not only on the segmented images, but really using that additional information that is inside the gray value image to recognize objects. And also involved in that project will be looking at image upscaling and super resolution approaches. And of course, covering all of the years, we will still work on making GeoDict even easier, get rid of some of the bugs or most of the bugs, and have general improvements to the software. In the next step, I would like to hand over to my colleague, Andreas Kriese, who is going to show you a presentation about how to analyze fiber length in a composite material. Andreas, here's the presenter.
Thank you. So, welcome everybody to my talk about digital fiber length determination of injection molded glass fiber reinforced composite materials. Easy title. To sum it up, we will talk a lot about FiberFind and what to do with it and how it works. I have to thank my colleagues, especially Nelly, Eric, and Anne, who is actually not on the slide here, who did quite a lot of work for this presentation and the results I will be presenting. Well, first of all, why are fiber lengths so important? Well, fibrous materials occur in a lot of different types of materials: fiber, media, insulation materials, medical products. We already heard about hygiene products earlier today, but also in composite materials for injection molded parts in cars and many other applications. And in all of these applications, they play a quite important role for the performance of the material. So if you have longer fibers, for example, in such a composite material, you usually end up with a stronger material in the fiber direction and, well, not so strong in the orthogonal direction. For all the other materials, it is also important for the material to keep together and stuff like this. So understanding what your fibers look like after the manufacturing process can be quite important, and especially for injection molded parts, the length of the fibers can quite drastically change during manufacturing. So to do the fiber analysis on a CT scan, we first of all need to do a CT scan. So now maybe an introduction for not everybody here is used to CT scans. How does it work? Well, you have on the left side X-ray tube that is emitting X-rays, and usually a cone beam for these applications through a sample that is the turning Lego figure here. And then on the right side, you have a detector that's basically a camera. And with that detector, you take images of the sample rotating, so-called projections. It's what you're seeing on the right on the screen. And you can reconstruct a 3D volume from these projections using a back projection algorithm, for example. And this is where we usually start with GeoDict. So we don't do that reconstruction stuff. We just load the volumes into GeoDict. And then what do we do with these volumes? Well, this is, for example, the workflow how it would look like for this fiber length analysis. We first start with the CT scan. We do a segmentation, and then we do the analysis. Here, for example, I have an orientation analysis, the fiber length result, and also an individual fiber identification. So how do we do this segmentation? Well, my colleague Mike already presented earlier today that we have this AI segmentation. Here, this is the example we will be looking at later. But in this example, we use the AI segmentation to segment the pores, the fibers, and the matrix. So we see on the top right, that's the overall sample we will also be looking at later. And in white, we have the matrix material. In gray, we have the fibers. And in red are the pores. And in the bottom, we can see how that in principle works. We have on the left side the original gray value image. Then we have some labels that were manually put in there. And then we get on the right side the segmentation that is then created using the AI. Well, in the context of this talk, the pores don't really matter to us. So we just did a straightforward segmentation using a global thresholding. And we can see here, this is the sample we will be looking at later again. It's quite a lot of fibers, and we have a change in orientation in the fibers. So in the top layer and in the bottom layer, the fibers are oriented in the direction basically into the CT scan, into the image plane, and in the middle they are oriented out of this plane. That's the process that usually happens with injection molding because the fibers orient themselves with the flow. So how can we determine the fiber length? Well, one method, of course, is experimentally based, and that was done also with the sample that we looked at earlier, using this FASAP system. There were for this system to work, you first of all have to somehow separate your fibers. So you ash the matrix in this case, burn it up. Then you get the fibers out of that remainder of your sample. You dilute them with glycerin, and then you put that mixture of fibers and glycerin into this machine that has a microscope in it and does an automatic fiber segmentation based on the 2D images of the diluted material. This system will provide a baseline we will compare our method with, and it's working according to some ISO standard that's listed on here. For experimental measurements, well, there are of course some problems. As I mentioned, you have to ash the sample. So you burn it, you cannot use it for anything else afterwards, cannot do another test with it. You have to somehow separate them, even if you don't have a composite with a matrix material, but for example, a non-woven, you have to pull out the individual fibers and you might break fibers. So you always end up with a bit of an error. And of course, it's labor intensive. So I have a bit of an overview slide. What other options do we have? As I mentioned, first option, the lab-based method. Second option, you can use some indirect method to get a correlation for the fiber lengths, for example, looking at cord lengths or a correlation of endpoints. But these methods will be limited to mostly straight fibers. You will have issues if your fibers are curved. But might also work with skins that don't have so much high quality. And well, finally, we have the way we do it in GeoDict, where we do an instance segmentation of all the fibers in a microcity. Instance segmentation means, well, each individual fiber gets a different ID. And well, once we have this instance segmentation, we can easily reconstruct each fiber as an analytic representation. We can measure length, we can measure orientation, curliness, whatever you need, we can measure it on there. Well, limitation is, of course, you need a good CT scan and some compute power. So how does FiberFind do this? Instance segmentation and length measurement. We start with the neural network that finds us the center line of each individual fiber. We then use these center lines. At that point, they are just basically voxels in a CT scan, and process it into a graph structure that we will analyze for errors and correct any errors that we might find, because, well, it's an AI method. You cannot directly control its output, and there might still occur errors in some cases. That's why we have this correction step. And then finally, we take this graph structure that is then hopefully only a list of voxels that make up center lines, and measure the diameters at each point and process it into a polygon list that can be represented inside of GeoDict as an analytical fiber. So why do we use a neural network? Well, I have an example here that I took from a CT scan of one of our customers. It's not a composite material, it's a glass fiber non-woven material. And as you can see, these fibers are very well entangled for, it's I think about 1 millimeter, and the fibers have a diameter of 6 micrometer. And then it's the question, how do we find a center line for these 3 fibers that we can use for our analysis? I prepared a bit of a comparison for different methods to find such a center line. First of all, we have on the left a simple morphological skeleton. And as you can see, it does not work very well. We have in the bottom, we have 2 center lines, then it merges to 1, have a bit of 2 center lines then again, but we never have 3 center lines. So basically this result we cannot use for anything. It's just not working if fibers are in such close contact. Then in the middle, I have a distance transform-based skeleton where we find the center line of a fiber using an Euclidean distance transform inside the fiber and basically search the maximum. And that already looks quite good. On the right side, we have the output from our neural network. And if we now directly compare them, well, on first glance, they look pretty similar, but then we see, okay, there is some issues in there. So we see in the middle, there's some kind of bridge forming where the fibers tangle around each other. and below the fiber is also breaking apart, while the other one is quite thick still. So there's room for improvement using some rich detection algorithm, but you will always end up with some errors. And now remember, this is a quite well-resolved scan. There might be worse scans where that looks way worse. And now if we look at the right side, at the output from GeoDict, there we basically don't have any errors. So well, you have to trust me a bit on that, because the fibers are entangled and we don't have a 3D image here, but there's no contact between these center lines and they are not breaking apart. And this is even before we have our correction step inside of FiberFind. And well, this is what the result looks like. We have on the left the original CT scan, and on the right then the image where we labeled each fiber with one ID, here represented as 3 different colors. So, second question that always comes with AI methods, well, how do you train it? And well, the lucky thing is we have FiberGeo. And with FiberGeo, we can generate a lot of different types of fiber structures. And we use that to create our self-artificial training data. Because for the fibers we generate with FiberGeo, we know where the center line is. So we can easily create images where we have fibers with their center lines encoded. And because the method in FiberFind works based on patches, so we always feed a 3D patch of the structure into the neural network, we also only need to reflect our training data needs only to be similar locally compared to the real data you will later apply it on. So it doesn't matter if we actually match, for example, the solid volume fraction and stuff like this, but what we need to cover is different shapes of fibers, how the contacts between fibers look, what kind of artifacts are in the CT scans, different orientations of fiber contacts, and all the stuff we can easily create with FiberGeo. And well, we did this for the neural network we have inside of FiberFind. I created around 100 structures looking similar to the one you see on the left here, where we have varying fiber diameters and stuff. And then we trained it for roughly 3 weeks on the current high-end GPU, but customer grade, no of these $20,000 H100s, just standard GPU. And well, that is the network you get with FiberFind, and it works for most structures. So now I have a few nice examples to showcase. So this is a very nice CT scan we got from the ITA in Aachen. It's a degradable ACL scaffold. So if you have that broken in your knee, they can make something like this. It's a 3D woven sample with 252 fibers in it. They are in 36 bundles. And we applied FiberFind to it. And as you can see, we can nicely separate the individual fibers, even though they are in contract for such a long time. And to showcase what we can do with this fiber identification, I also clustered the individual fibers in the bundles we have based on their distance from each other. And get a nice clustering of the individual bundles that we can use to visualize, for example, how the bundles turn around each other and traverse through the overall structure. And second nice showcase I have was taken from a very, very big non-woven sample that was about 10,000 by 5,000 by 2,000 voxels at a resolution of 1.4 micrometer. And we segmented all the individual fibers in there and searched the longest. And Steffen, actually, he's over there with his camera, created a video where we follow the longest fibers throughout the whole structure. And as you can see, that works very well. We have where the fiber separated cleanly from the other fibers, even though it is a very complex geometry, it curls around a lot, it has a lot of contact with other fibers, a bit different from the sample where we saw before, where they are all constantly in contact. Now we have random contact points with different fibers. And yeah, as you can see, FiberFind did very well here. I think so. Enough of this fiber goes on for a bit. So now to get back on our actual example we wanted to talk about, we have again many fibers here, so way more fibers than in the sample before. Simpler geometry because they are just a bit curved, they don't curl around. Nothing there has a real loop in it. And well, this is the very colorful result where we have different IDs in each voxel of the fibers. And we can see, okay, FiberFind can separate these fibers very well, and we can analyze them. And we analyzed the fiber length and compared it to the result of the FASEP system I told you about before. And the FASEP system ended up with a mean fiber length of 1.6 millimeters, and GeoDict came out with 1.58 millimeters. So we are very close to our baseline we defined, with only a deviation of 2.8%. These measurements were done in the DigiLogB project that GeoDict is part of, and there are also some posters about that project in the poster session. So if you want to have more details on this, you can look at the posters later on. You can also see on the right side, we have the fiber length histogram. We also have a very good agreement there. It's only slight deviations. In blue, that's the result from FiberFind. And in brown, that's the result from the FASEP system. We have a very good agreement. And of course, because we have the individual fibers, we don't not only get the fiber lengths, we get also diameter distributions, orientations, curvatures, and curliness. And for that, I have also another slide. Here we see again the sample, this time a cutout, and that we can actually see something where the fiber orientation was measured, and we can nicely see that change I talked about before, that we have on top a layer that is oriented in one direction, then in the middle a change in direction, and in the bottom it's the other way around again. And on the right side, we get that also as a nice curve going through from top to bottom. We can see that the angle of the fibers changes from 30 degree to the x-axis to 70 degree in the x-axis and back again. For this, we also don't need to do the individual fiber identification. It's just a byproduct in the FiberFind module, but we also have a method that is only based on PCA or star length distribution that has the advantage that you don't need that high resolution. So FiberFind, usually you would like to have at least 4 to 5 fibers, voxels across the fiber diameter if you push it. So ideally it's more like 5 to 6. And for this fiber orientation, we can work with even less. And last but not least, same for the fiber diameters. Well, it is a byproduct in the fiber identification, but we also have a method that is working directly on the image without fiber identification that also doesn't need that high fiber resolution to work reliably. With that, I want to thank you for your attention, and I'm open for questions.
Welcome back, everyone. We are going to restart the session right now. And the next talk will be from my colleague Lilli Burger. She will show you a little bit of an insight on how to get from a 2D SEM image to a 3D model for nanofiber media. Please, Lilli, go ahead.
Thank you, Oliver. So also from my side, welcome back to the second part of our breakout session, Fibrous Materials. My name is Lilli Burger. I'm an application engineer at Mass-to-Market support team. And today I'm going to show you how to model a 3D digital twin on the basis of a 2D SEM image. But let me first start with a short introduction. So here you can see the exemplary development process, which you already have seen in the introduction before. Usually, a digital material workflow starts with importing a 3D image of a physical sample. We have heard a lot about importing and segmentation functionalities of GeoDict before, so I will keep that short. However, in the context of nanofibrous structures, it's hard to obtain a 3D image which is of sufficient resolution and by using conventional and affordable methods. So often you only have 2D images. And we also seen on the roadmap in the introduction Oliver gave us before that there are development steps planned for an automated 2D to 3D model. However, today I'm going to demonstrate to you that even now it is possible to easily and straightforward extract information from the 2D SEM scan and model a full 3D digital model. So let me switch to GeoDict. First, we have to import our 2D image with our import GeoVol functionality. I've prepared an example of a nanofibrous filter media. And here you can see the geometry import dialog opens, and we have here our dimensions of the image domain. We can crop that, but for our application, this is not necessary. Furthermore, you have to set the voxel length. As we don't know that yet, this will be one of the first steps we have to go. We will write a dummy value 1 and go on image processing. Then we might have to change the visibility, and you can change here the orientation, top to bottom. And you see now the image is imported. So as already said, we do not have the correct voxel length. So this will be the first step to go, and an easy way for that is to use the scale on the image as an orientation for that. So we have to zoom in again, zoom on the scale bar, and then you can use the measure distance and angles functionality of GeoDict. We switch to angle and distance here and measure the length of the printed scale by first clicking at the start point and at the end point of the scale, and then adjusting the auxiliary line such that we have about 90 degrees here. For better visibility for you, I will change the color of that line and the thickness. So I hope this is better now. Okay. Here at the right-hand side, you also can see the length of the distance and the angle better. Now to adjusting the voxel length, we have a button here. Go on there and activate the set voxel length according to the length of the marked line. And from our image, we know that this line should be 2 micrometers long. We can set this in this dialog and go on OK. And now you can see in the left-hand side at the status area that the voxel length has been adjusted according to our step. Now we can move or zoom out again a little bit. So the next step is to measure the fiber diameters. So because we want to generate a 3D model, one important parameter, of course, are the fiber diameters. Therefore, we can use this measure angles and distances functionalities. Once again, we recommend, of course, measuring as much fibers as possible for you to get a good overview about the distribution of the diameters. For this demonstration, of course, I will leave it at 1 or 2 fibers. But yeah, let's find fibers in the foreground of the figure. We can use these two and start the measuring process. Again, clicking at the starting point and then at the end point, and adjusting the auxiliary line. It is important that we have about 90 degrees here, so that we don't measure a diagonal and a fiber diameter which is too long. Now this fiber diameter is about 240 nanometers. You can see that on the right-hand side. And the second one, maybe once again, auxiliary line. And now you see I have to adjust my measurement line such that we have again 90 degrees. And here we have a little about 232 nanometers. So we have done this with all or with many fibers, and the mean value of all diameters was about 250 nanometers. We will keep that in mind and switch to Model Fiber Geo for the structure generation step and choose Create Fibers. Go on Edit, and the dialog opens. So at the bottom of this dialog, we have to enter the domain size in voxels. So here we know from our image that we have 720 voxels in X direction, 480 in Y direction, and in Z direction we do not have any information. So we just want to be the structure 300 voxels deep. Now our voxel length, we know from the step before, it's 16. It's about 60 nanometers, but for a more convenient input, let's switch to nanometers in the scale area. So now we just can set the voxel length directly in nanometers. At the bottom of this dialog, we have some generic criteria. We will leave the generation and overlap mode to allow fiber overlap at the default value. And at the right-hand side, we have some stopping criteria. Here also, I want to use the default setting, the object volume percentage. This means that the fiber generation process stops as soon as 10% volume percentage is reached. As we do not know for our structure what is the exact porosity, we keep that at the default value, and later on we might have to redo this step, so there is some kind of iteration planned. The second tab, the fiber options, allows us to define the shape of the fibers. So we do have only one type of fibers and can remove the second default fiber type, and we say 100 of all fibers which will be generated will be of one type, and material should be polyacrylonitrile in our case. Of course, you can add as many types of fibers as you need, and you also see here all fiber types which are available. On the right-hand side, we enter now the fiber diameters in nanometers, which is about 250. But once again, we have different options here. You not only can set a constant value, you also have the possibility to enter a distribution, for example, uniformly in interval or some stochastic distributions. The last part to set for the fiber shape is the orientation. We have seen in the figure that the fibers seem to be mostly parallel to the XY plane. So we will change the orientation to the anisotropic direction mode and use a high value for the first parameter. Okay, then the other tabs we will leave at default, and now we can start the first structure. And as you can see, it doesn't look like our structure as our image. So we first have to change some visualizations. First of all, set the background color to black and the fiber color to gray. Also, you can change the depth of the visualization to get a more SEM-like view. So now this looks more similar to our image, but we also have a 3D view now, as we have a 3D model now. And here you can see that some of the fibers at the border of the domain are cutted alongside. So this is something we want to change in the next step. Therefore, we can use the process geo embed functionality. So you have here the option crop, embed, and add layers. Go to embed and open the dialog box. And then you can add some space to the bottom of your domain in that direction. We can add also some space in that plus direction. And an important step is to embed also the analytical objects, which are our fibers. Run. And now you can see we have a full 3D structure without cutted fibers. Now, as we do not have all parameters for our 3D model, we might have to change some of them and redo these steps. Therefore, first, let's check the 2D image of our generated structure. And here we see that the porosity is way too high compared to our figure, which we had before. So we go back to Fiber Geo and change the object volume percentage to 22. You might have to redo this step. We know for our application, 22 is a good value. Also, in our generated structure or in the image, we see that the fibers are more directed in Y direction, oriented in Y direction than in X direction. So we also change the second anisotropy value. And let's see how the result looks like now. And now we see it looks much better. I will open the image. So this is the original image, and here we have our 3D model. And yeah, but this time not only in 2D, but we have the full 3D image. Just redo the embed step. Okay. So that's it from my side. Thank you for your attention.
Okay, so we are approaching the end of the session. Thank you for attending. Thank you for your, sorry. Thanks for being here. Thanks for discussing with us. Have a great day.